So in today's video, we are going to look at the point set, intervals, absolute value equations, and inequalities. Now, in the introductory video to this course, we learned that each real number corresponds to a particular point on the number line, and for that matter, every point on the number line also corresponds to a real number. Now, a set of points or real numbers located on the real axis is what we call a one-dimensional point set. Now let's move on to what an interval is. An interval is said to be the set of real numbers or which lie between two real numbers. So an interval is nothing but the set of real numbers that can be found between two real numbers. Now let's assume that we have two real numbers, a and b. So let's assume that a and b are two real numbers, and a is said to be less than b. Now, using this notation, we can define the various types of interval notations, and these interval notations are classified based on their endpoint. So let's look at the various types of interval notations we have. 1. Now, the set of real numbers x such that a is less than x is less than b is called an open interval. And this interval can be represented in the interval notation as a comma b in a round bracket or parenthesis. Now, an open interval contains all the points between a and b, while a and b themselves are not parts of the set. 2. The set of real numbers x is such that a is less than or equal to x is less than or equal to b is called a closed interval. It's called a closed interval, and this can be represented in the interval notation as a comma b in a square bracket. Now, this type of interval, which is the closed interval, contains all the points between a and b themselves are part of the set. So for a closed interval, a and b are included in the set. Now, the difference between an open interval and a closed interval has to do with the inequality sign. You realize that for an open interval, we have a less than x, x less than b. However, for a closed interval, we have a less than or equal to x, x less than or equal to b. So in an open interval, because we have a less than x less than b, that is why we have a comma b in parentheses or round brackets. And for a closed interval, since we have a less than or equal to x, x less than or equal to b, that is why we have a comma b in square brackets. So this is the main difference between an open interval and a closed interval. For an open interval, the endpoints are not part of the set, whereas for a closed interval, the endpoints are part of the set. Now let's move on to another type of interval notation, that is the half open or half closed interval. Half open or the half closed interval. A half open or a half closed interval is a type of interval which is closed at one end and opened at the other. Now we have two types of this interval. One is the set of real numbers x such that a is less than or equal to x, x is less than b. And this interval can be represented in the interval notation as, now because we have a less than or equal to x, then on the left hand side we are going to have a square bracket and then a comma b, and then on the right hand side, because we have x less than b, that is going to be a round bracket. And because the interval is closed on the left hand side and then opened on the right hand side, we sometimes call this the closed open interval. So with this type of interval, A is included in the set, whereas B is not included in the set. Now to the second one, we have the set of real numbers. X is such that A is less than X is less than or equal to B. So we can as well represent this in the interval notation as round bracket A, comma B, square bracket, because we have A less than X, X less than or equal to B. And because this interval is open on the left hand side and then closed on the right hand side, we call this the open closed interval. So also for this type of interval, A is not part of the set, whereas B is part of the set. Now all we've discussed so far are called bounded intervals. So what then are bounded intervals? An interval is said to be bounded if there are some real numbers that is smaller or greater than all its elements. So let's assume that we have a given interval. So if there are some real numbers smaller than all the elements in the interval, then we call that a left bounded interval. And if there are some real numbers greater than all the elements in the interval, then we also call that a right bounded interval. Now what happens if this interval is both left bounded and then right bounded at the same time? Now if you have that situation, then we call that interval simply a bounded interval. And a bounded interval can as well be referred to as a finite interval. So once we can make references to bounded intervals, then we can as well talk about unbounded intervals. Now unbounded intervals are nothing but the direct opposite of bounded intervals. So we have what we call the left unbounded interval as well as the right unbounded interval. So left unbounded interval and right unbounded interval. Now an interval is said to be left unbounded if there are no real numbers smaller than all the elements in the interval. Now an example of such interval is negative infinity, comma b, which can be represented as x is such that x is less than b. Now such interval is a left unbounded interval simply because there are no real numbers less than negative infinity. Now to right unbounded intervals, right unbounded intervals. An interval is said to be right unbounded if there are no real numbers greater than all the elements in the interval. Now a typical example is the interval a, infinity, which can as well be represented as x is such that x is greater than a. Now in this interval, we do not have any real number which is greater than infinity. So this is an example of a right unbounded interval. Now if an interval is left unbounded and right unbounded at the same time, then we say that that interval is unbounded at both ends. So that interval is unbounded at both ends. And a typical example of such interval is the interval x is such that x is the set of all real numbers, which can be represented in the interval notation as the open interval negative infinity, comma infinity, or better still, the closed interval negative infinity, comma positive infinity. Now let's move on as we solve some absolute value equations and inequalities. Now let's try to solve these problems. Now even before we do that, there are some properties of absolute value equations and inequalities that we need to consider. So let's consider these properties. So given that x is a real number and a is a non-negative number, 1. The absolute value of x is equal to a if and only if x is equal to plus or minus a. 2. The absolute value of x is less than a if and only if negative a is less than x is less than a. 3. The absolute value of x is less than or equal to a if and only if negative a is less than or equal to x is less than or equal to a. 4. The absolute value of x is greater than a if and only if x is greater than a or x is less than negative a. And then lastly, the absolute value of x is greater or equal to a if and only if x is greater or equal to a or x is less than or equal to negative a. So basically these are the properties that we are going to use to solve these problems. So let's try question 1. So we have the absolute value of 2x minus 3 equals 7. So how do we solve this problem? So from property 1, you realize that we have the absolute value of x equals a if and only if x is equal to plus or minus a. So to solve this problem, we are going to apply property 1. So that's going to be 2x minus 3. That is, we are going to remove the vertical bars, and that will be equal to plus or minus 7. So we are going to obtain two equations here. So the first one is the equation 2x minus 3 equals 7, and the second is 2x minus 3 equals negative 7. So let's solve the equation on the left hand side first. So we have 2x equals, we transpose negative 3 to the right hand side, we have 7 plus 3, and that is equal to 10. Now we divide through by 2, and then we have x equals 5. And for the second equation, we have 2x equals negative 7. We transpose negative 3 to the right hand side, and then we have plus 3. Now 2x equals negative 7 plus 3 is negative 4. We divide through by 2, and then we have x equals negative 2. So now we can say that the solutions to this equation, that is the absolute value of 2x minus 3 equals 7, are x equals 5 and x equals negative 2. Now let's solve the second problem, that is the absolute value of 2x plus 4 less than 2. Now you realize that this is similar to property 2, so we can apply property 2 here. That is, the absolute value of x is less than a if and only if negative a is less than x is less than a. So this time we have this to be our x and then this to be our a. So that's going to be negative 2 is less than x, and then in place of x this time we have 2x plus 4 is less than 2. So at this point we can generate two inequalities here. We have this to be the first one, and then this to be the second one. So let's solve the two inequalities. So for the first one we have negative 2 less than 2x plus 4. Now we transpose 4 to the left hand side, and that becomes negative 2 minus 4 less than 2x. Negative 2 minus 4 is negative 6 less than 2x. We divide through by 2, and then we have negative 3 less than x, or better still, x greater than negative 3. Now let's solve the second inequality. So that is going to be 2x plus 4 less than 2. So we transpose positive 4 to the right hand side, and that becomes minus 4. And then we have 2x is less than negative 2. We divide through by 2, and then we have x less than negative 1. So we have x greater than negative 3, x less than negative 1. Now we can rewrite this as, we have negative 3, so negative 3 is less than x, and then x is less than negative 1, so less than negative 1. And this can be represented in the interval notation form as an open interval, because we have negative 3 less than x. So open interval negative 3, comma, and also we have x less than negative 1. So we have comma, negative 1, also open. Now since both sides of the interval is open, it means that negative 3 and negative 1 are not part of the set. Now let's take some more examples. So let's try this problem also. We are going to solve the inequality and determine its interval. So we have the inequality. The absolute value of x minus 3 is greater or equal to 2x plus 5. Now to solve this question, we are going to apply property 5. Now property 5 says that the absolute value of x is greater or equal to a if and only if x is greater or equal to a, or x is less than or equal to negative a. So we are going to apply this property to solve this inequality. So we have a to be 2x plus 5, and then we have x to be x minus 3. So for x greater than or equal to a, we are going to have, we have x to be x minus 3 greater or equal to a, that is 2x plus 5. Now let's solve this inequality. So we transpose 2x to the left hand side, so that we have x minus 2x is greater or equal to 5, and then we transpose this to the right hand side, that is negative 3 to the right hand side, and then we have plus 3. So this becomes negative x greater or equal to 8, and then we divide through by negative 1, and then we have x, and because we divided through by a negative value, the inequality sign is going to change, so that we have less than or equal to negative 8. So we say that x is less than or equal to negative 8, or for the second inequality, that is we have x to be x minus 3 is less than or equal to negative a. So that is negative into bracket 2x plus 5. So let's simplify. So this becomes x minus 3 is less than or equal to, we multiply negative 1 across, then we have negative 2x minus 5. Now let's transpose negative 2x to the left hand side, so that we have x plus 2x is less than or equal to negative 5, and then negative 3 becomes plus 3. So we have 3x is less than or equal to negative 2. We divide through by 3. And then we have x is less than or equal to negative 2 over 3. So we have the solution to be x is less than or equal to negative 8, or x is less than or equal to negative 2 over 3. Now our task here is to investigate which of the solutions satisfy this inequality. So first of all, let's represent this on the number line. So we have this to be our number line. We have this to be negative 8. And then we have negative 2 over 3 somewhere here. So since we have x is less than or equal to negative 8, then we are going to have a solid circle. And then because it's less than or equal to, it means it's going to the left. And then also for x is less than or equal to negative 2 over 3, we also have a solid circle and also moving to the left. Now at this point, let's try to test the values in between negative 8 and then negative 2 over 3 to see if we can get a value here that will not satisfy this inequality. Now it is very important to verify whether there is any value in between these 2 points that does not satisfy this inequality. So let's choose any value. Let's choose any value, say negative 3. So let's choose x equals negative 3. So let's say for x equals negative 3, let's put this into this inequality. So we have the absolute value of negative 3 minus 3. That becomes negative 6. And that will be greater or equal to, we have 2 times negative 3. That will be negative 6. And then plus 5. Now negative 6 plus 5 is negative 1. So we have negative 1. Absolute value of negative 6 is 6. And you realize that 6 is greater than or equal to negative 1. And this is correct. So it means that x equals negative 3 satisfies this inequality. So it is likely that all the values here is going to satisfy this inequality. Also, let's test for any value after negative 8. So that can be negative 9. So let's say for x equals negative 9, we can have negative 9 minus 3, which is negative 12. So we have absolute value of negative 12 is greater or equal to, now 2 times negative 12 is negative 24. And negative 24 plus 5 is negative 19. Now you realize that the absolute value of negative 12, which is 12, is greater or equal to negative 19, which means that the values after negative 8 also satisfy this inequality. Therefore, the solution to this inequality starts from negative 2 over 3 inclusively towards negative infinity. So we say that the solution to this inequality is x is such that x is less than or equal to negative 2 over 3. And the interval is negative infinity, that is an open interval on the left, comma, negative 2 over 3. And because negative 2 over 3 is included in the set, then you have a closed interval at the right. So that's it for today's video. Thanks for watching and see you in my next video. Bye bye.